All right, midterm. Okay, so this is using polar coordinates here. It's a good system to use when you have non-circular motion. Spiral motion especially seems to work well with polar coordinates. You put the origin of the coordinate system at the center of the spiral and then measure out from there. So we got a couple of these, 150. I'm always renumbering these. I don't know if it's 1 or 2, but it's this one. It's the one with the ant on a plate kind of thing, walking outwards. Yeah, I think it's 151, right? Okay, so now the sequence on this stuff, from my point of view, is first recognize what it is. Okay, so that's a spiral problem because it's got a rotation plus an outward motion. So when I see those two things, what I start to think of is a spiral. Okay, so that's the first thing I want to do. The second thing I want to do then is say, okay, if it's spiral, I'm going to use polar coordinates. And then after that, if it's polar coordinates, I've got to find 5 or 6 things. Okay. And the things are the variables you put into the polar formula. Now the polar formula is shown on the upper left-hand part of your formula sheet. I don't know, maybe a third of the way down or something like that. So have a look at it so that you know what it looks like. And so what you want to do is find r dot, theta perhaps, if you may or may not need it, theta dot and theta dot dot. Okay, so that's what you want to find. So the first thing I do is just make a little chart, get all that stuff filled in, and then I plug it in. Okay, and I do that because I've mentioned before I'm not really all that bright, and it helps me to have these little kind of crutches to help me make less mistakes. Okay, so that's how I look at that. All right, so what we've got here is an ant starts from rest on the center of a flat rotating disk and walks outward with an acceleration of 0.2 meters per second squared. Okay, the disk starts rotating at the instant the ant starts to walk and has a constant angular acceleration of 1.2 radians per second squared. Okay, so what we've got there is we've got r dot dot. Okay, and what that equals is 0.2 meters per second squared. And we're also given theta. It's an acceleration, so that's theta dot dot. And what that is 1.2 radians per second squared. And notice that the units look pretty good there, don't they? Because they're, I've got r dot dot, which is a change in length at meters per second squared, and theta dot dot, which is a change in angle in radians per second squared, okay? All right, so I think then what I'm going to do here is kind of walk it on back and get to r dot and theta dot is probably what I'll do. Now what I know is I've got r dot dot. Now what dots are time derivatives, okay? So you want to remember that. A dot signifies a derivative with respect to time. So for instance, what I've got here is dr dot dt, and that equals 0.2. So dr dot is equal to 0.2 dt. All right. And then I could integrate that. So I'll integrate that from 0 to t and from 0 to r dot, because that's, I'm starting with both of those at 0 and then working my way back. Okay, so that's what I'm up to here. So what I've got there, again, I've got r dot dot is equal to 0.20. Now what that is dr dot dt. Okay, so I'm taking a time derivative of r dot, and that's equal to 0.20. So dr dot is equal to 0.20 dt. All right, and then I'll integrate, and I'll go from 0 to r dot, and I'll go from 0 to t. So the integral of dr dot is r dot, which is just a velocity. I kind of like to freeze frame this stuff in my mind. It helps me to kind of put together what's happening. So what I've got there is the acceleration of the ant walking outwards. When I integrate it, I get the speed of the ant walking outwards. Okay? And when I take the derivative, or excuse me, the integral, the antiderivative of 0.2, I'll get 0.20t. And then I plug in my limits and I get r dot is 0.20t. Okay. Are we okay with that? So if you take 0.2 times whatever the time is, you get the speed of the ant walking outwards away from the center. When you combine that with the rotation, that's why that's a spiral. Okay. So what you're doing there is you're taking this plus that, and what you end up with is that. Okay. That's what's going on. We all good with that business? Okay. And then what you get from there is dr dt, which is what r dot is 0.2t. So you can walk that back and get the position, which is 0.1 t squared. Okay. All right, so you just kind of do some integration there and work your way back. You can also get from theta dot dot back to theta dot, okay? So you're given that theta dot dot is, whatever the heck it is there, it's just straight 1.2. So from there you can integrate back, just as I'm doing up above. And you can get back to theta dot. And that'll be 1.2t, okay? There you go. So I just get all those things identified, that those are the 5 things that I need to put into my table. I notice that I don't need theta on this one. Okay. So we got any questions on this stuff? You doing okay? Okay. All right. All right. So the next thing I do then is I just make myself a bit of a table here. So I got r dot, I got r dot dot, I've got theta dot, and theta dot dot. And then I just put in what they equal. And, you know, just get a little table going here. So, you know, 0.1 t squared, 0.2 t, you know, et cetera, et cetera. Cool. And then I'll just find what's going on when t equals 3, okay? So I'll plug in 3, and this will be 3.6 and 1.2 and 0.2 and 0.6, and 9 times 0.1 is 0.9. There we go. So now you got the numbers, and you just plug them into the equation. That's how that goes. So what we're doing on that is we're just doing integrations. We're given the accelerations, and we just integrate back to velocity, and then to position, basically, for R. And then when you've got these, you just plug them in, okay? So we're just going to plug them into those equations and get the answers out. okay? Any questions on that? Okay. All right. So that's the basic drill on this stuff. Okay, now so what we get if we find these velocities, then, if we're good on that, is we get a radial velocity and a transverse velocity. So let's all think about this for a second. What are the units on the radial velocity?
Radians per second.
Yeah, that's why I'm bringing this up, because it's often, we want to be sure we understand that. That's a V, right? It's not a theta dot, or if you're in physics, it's not an omega. So that's meters per second, okay? Now, how about the units on V sub theta? What are those? Yeah, see, and that's especially why I'm bringing this up. And I think the problem is the notation. What people see is they see that theta, and they think it means angle, but it doesn't. It means transverse, okay? So the units on the V sub theta, what that is, that's the transverse velocity. The units on that are meters per second, okay? And I'm not, I'm not trying to call it, I just want to ask that in a question form, just because I figured probably half or more of you would come up with the wrong thing. And I just want to bring that up because it comes up a lot, okay? So velocity, it's a V, that's the thing to focus on, and V is meters per second, okay? And it's the same thing with the A, okay? So A has a radial component, but that's meters per second squared. And then this, again, that thing looks like an angular acceleration or something, but it's not. That theta means transverse. So that's meters per second squared also, okay? So just remember that, okay? Because it's a very common misconception that comes up on this stuff. So I just want to point that out, okay? So just watch those units. And, the units are often helpful in knowing how to put stuff together. And if you have the wrong units, it can be confusing on how to put stuff together. So I just want to call that out. Questions on that? We're doing okay? Okay. We got another one here. We got a car traveling along the spiral section of a road. Spiral path of the road is described by the equation, and we give you the equation there. R equals 380 theta meters with theta in radians. The angular velocity of the car is a constant. And, this is basic kind of word problem, stuff. So angular velocity of the car is a constant. The word constant is important. 0.4 radians per second in the direction shown. So that looks like counterclockwise. Find the radial and transverse components of the velocity and acceleration of the car when theta equals 60. Now watch it though, because we've got theta in radians. And so 60 is what? Is that pi over 3? But of course we wouldn't use anything like pi over 3 because we're engineering types, so we don't do that. We call pi over 3 1.05 or 1.047 or something like that. Okay. And then we want to find the components of, of velocity and acceleration. We also want to show them on the sketch, okay, and find their magnitude. So remember to show them on the sketch. I give you a couple extra sketches on that sheet I made up for you. These right here. So go ahead and show those things in their proper orientation on those sketches there, okay? So remember to do that. All right, so do we got any questions on how to do this one? Give you a little hint if there aren't any questions, because sometimes When I'm met with this level of silence, it means people haven't looked at it too much every now and again. That happens sometimes. Very rarely, I know. Once every other blue moon, I think, perhaps. Maybe. Okay. So what we do here is we have, that's what we got for R, okay? Now see, now the thing is, don't get too hung up on, doing a bunch of fancy algebra or trig or something here. What's theta right now? When we want to know what R is? Okay, you got theta, you got the function, plug it in, you're done, okay? That's it, okay? You just plug in theta and you'll get what R is, okay? Okay, now what's theta dot? No, let's back up a second. What is theta dot? If you had to define it, if I gave you a short answer quiz on this stuff and I said, what's theta dot? What two words would you write in for the answer? Angular velocity, right? Now, what are the units on theta dot? Yeah, radians per second. See, this is radians per second because it's not V, it's theta dot. So that is in radians per second, right? So keep that in mind. You put that into the formula to find V, but V is R theta dot, right? The rate of distance in meters times theta dot. Okay? So keep that. Just kind of keep this stuff in mind. Okay. So what's R dot then? I mean, yeah, it's the velocity kind of in and out towards the center. Yeah, it's called the radial axis. What's the number going to be on that? Or what do we fill into that first space there?
Do we take the derivative of the R first?
Yeah. How do we take the derivative of the R? What do we got? Yeah, right. See, I guess the short answer to what is the derivative of that is I don't really care all that much, okay? Because I know it's 380 theta dot, and I know what theta dot is. You're given theta dot, just plug it in, you're done, okay? So this is, a little different maybe. Sometimes we kind of go into this autopilot thing where we want to start doing all the triple integrals with respect to e to the pi and all that kind of stuff. Well, no, just theta dot, plug it in, get on with your life, okay? That's kind of what I'm trying to say, okay? Okay, we good? Okay, because we're more about engineering than we are about teaching calculus and stuff, okay? I just want you to kind of understand and plug it in. Honestly, when you start working, you're the calculus gets toned down a little bit when you start working. Let's just say that, okay? It's more about understanding what you're doing than it is about the triple integrals and stuff like that. Okay? That's more the point, okay? So there you go. All right. So we got any questions on the homework then? You doing all right? All right. So that's due tomorrow. Okay. All right. Now we're looking at pulleys here. This is on that page. Was it 241 or something? I think it was. I honestly don't remember what page it was. 241. Okay, thanks. Why don't you give that a crack? Just take a couple minutes and try and set that thing up. Look at the example right up above. What you're going to do is write a simple expression for the length of the rope. You can eliminate the constants. The constants are typically wraps around pulleys, extra little lengths that don't change. You measure from a set point, and you can measure vertically or horizontally, whichever you'd like. Okay. Let's see that in 241. It's not in the homework. It's in that section ahead. So go like.
Yeah.
There we go. See now
Oh,
you're.
okay.
Yeah. Okay. So yeah, it's 241, and just write up an expression. How long is the rope? And put dimensions from a set point. Okay. And then dimension it out, and based on those dimensions, go up with an expression for the length of the rope. Okay. It doesn't look to me like point E's moving anywhere, so that might be a good place to measure from. You can measure from, there's other places you could measure from, but that's one place you might start. Doing all right with that one? Okay, so I'm measuring from point E there, from E vertically down to C. I'm calling that DC. Now there is a little bit of a constant on part of that. I'm kind of got that colored in the squiggly green line there. Same thing from E to A, I'm calling that DA. I've got a little bit of a squiggly green line in there from E horizontally to B. So the length of the line is 2 times DC. Now that little green squiggly constant, you know, I'm just ignoring it. You don't need to put them in, because when you take that time derivative, they're constants, they just go to 0. And then dA, take a time derivative, L goes to 0, DC goes to VC, and dA goes to VA. Then algebraically work it out. VA is 2.4, so VC is minus 1.2. I'm dimensioning that down, so the negative means it actually acts up. Yeah, of course.
So the parts of the rope that stay constant are the parts that can't be pulled out.
Can't change length. Yeah, I guess. Yeah, I mean, and they're not. I mean, so the constants on this one, I know I'm going to relate E to C to C to B. You know, that's going to be the same length as far as I'm concerned. It's kind of a doubling around the pulley. So I'm going to make that top little distance from E down to there a constant, because I don't want that to confuse my relationship, you know. Essentially, they're equal. I guess the reason is they're equal is they're going to change at the same rate. Okay? So I guess it isn't quite as simple as you stated, as I understand it. I mean, because the other constant is from E going out here to A. The constant's right in here, which isn't a rope at all. It's a blank space. So it makes it hard for me to really say yes to what you just said. You know, it's not always that way, I guess. And I don't know a nice little way to say it. The constants are always there, and they don't change. Commonly, they're wraps around pulleys, but they also might be little gaps in the rope or extra lengths of rope that just don't change. Now, the other little bit on that is you got one rope and you're coming off from A to B, and you got 2 ropes wrapping around the pulley at C, so that gets you a 2-to-1 ratio on how the ropes change length, right? I mean, it's nothing more complicated than that, really. We're making it a little bit more formal in how we're approaching it, but you know, if you get into a really complex block and tackle with multiple ropes, this type of method you'd need to use it. On the simpler ones, you can just look at the wraps, you know. There's 2 sides, there's rope going down to C and coming back up, that's 2, and then you're pulling it at A just once, so one length there, so it's 2-to-1. Ratio. That's really all that's going on there. But I've seen problems, you know, I have seen block and tackle that get pretty involved, and I've seen problems in statics and dynamics books where they get all these crazy pulley systems with lots of ropes. And you know, I think an approach like this would work best for something like that. All right, are we okay with that? Any questions on that one? All right. Okay. So that's a little bit on pulleys there. Okay. All right, we're going to look at a different topic, which I guess is the next page. It might be 250. It's relative motion. Yeah, 250. Now, this is a simple version of it. We're going to get into more complicated relative motion and use this quite a bit later when we look at like mechanisms. So it's kind of definitely a mechanical engineering kind of thing for the most part. If you look at like an internal combustion engine, you know, you can start at the RPM of the crankshaft. You've got a little bit of I don't know if you quite call it a cam, but you know, a lobe or whatever sticking off of that. You got a connecting rod going to a piston. So you can start with the RPM of the crankshaft, look at how far the cam extends, or not really a camshaft anymore, but you know, how far the lobe extends out from the center of the crankshaft, get its linear speed, look at how that pushes the end of the connecting rod, one end, then find the velocity of the other end of the connecting rod, and then look at how fast the piston moves and all that kind of thing. You know, that's kind of the advanced version of what we're starting here. So, but we're going to start with a simpler version of this, just dealing with points. You know, but but we'll build on this later, okay? So I want you to do this kind of in a standard sort of way because it'll help you when we do the more complicated version of this down the road. So let's say we've got an airplane flying away from a reference point, and for whatever reason we want to track the velocity of A as it moves with respect to that reference point, which you might think of being the absolute motion of A, the absolute velocity of it. Now that could obviously get a little complicated because the propeller's spinning there and the plane's moving, and you'd have to account for all that stuff as you work your way, to get that motion defined. Okay, now how you might approach this in a simpler way is what you're doing, you're finding the velocity of A with respect to the reference point. And so what we have here is you could establish an intermediate point, and I know that orange stuff probably isn't very visible to you. And I improve on that and try and make it blue without screwing things up here too much. So here's point B. So the motion of B, it would basically be what I would call a translation, which is just kind of a straight motion or a simple curved motion. Okay? So that would be just the motion of the overall plane moving through space. And I would call that a translation. Maybe a parabolic motion or a straight line motion or something like that. Okay? And so that's a fairly simple motion. Now, if you look at the motion of A with respect to B, that's a pretty simple motion too. That's just a rotation. Okay? So even though the overall motion of B is kind of complicated, the two component motions that go into it are pretty simple. So if you want to get the overall motion of A, call it, we're looking at velocity here, so we'll call that the velocity of A. What we could do is take the velocity of B as a vector and then add the velocity of A with respect to B to it. Okay? That's the idea. So the use of this to us is we can take complex motions and break them into little steps and add them together. And that's how we can figure out a complex vector motion. Okay? That's the idea behind this. So we can start with that. That's the overall idea. Okay. Now the actual steps in doing this, there's another little derivation I've got there on page 250 where we kind of walk it down, and we can start with a position. And I think relative position is probably the easiest of the bunch to understand and look at. Okay, so if we've got a relative position there, what we've got is, let's say we want to identify where B is, okay? Well, we could just measure a straight line from the origin out to B, and that would be RB, easy enough. But we could also do it another way that relates to relative motion. In this case, it's relative position. We could put an origin up here at A and get the position of B with respect to A. And I'll call that RB/A. And then I can figure out where A is. So if I want RB, I can take RA and add RB with respect to A to it, and I'll get the position of B. Okay? That's relative motion, relative position in this case. Okay? So if I know RB there is 5, 3, that X is 5 and Y is 3, and A is 3, 4, how I get from A to B is I go 2 in the X and -1 in the Y. So 3 plus 2 gets me the 5, and 4 minus 1 gets me the 3. Okay? Pretty straight up. Now, and the way that I kind of remember this is I look at the subscripts. If I've got, and I remember this notation that RB with respect to A That's how is said in that way and written like this, B/A. So that's B with respect to A. That's the meaning of that subscript. Okay. Now, the way I remember this is if I take the subscripts out and put them into a little algebra equation, I'll get B on this side, A over here, and then I can put a multiplication in there and times B over A. So A times B over A is B, so B equals B. That's how I remember to get those subscripts set up properly. Okay. All right, so that's relative position there. Now, just like we were doing with our pulleys here, I can just take time derivatives. So I can take our time derivative of relative position and get relative velocity if those points are moving. So VB is VA plus VB with respect to A. And similarly, I can get AB is A sub A plus AB with respect to A. Okay? So this relationship holds for position, it holds for velocity, and it holds for acceleration. Okay. Now it is important that the way you set up the vectors matches your equation. So I've got a little equation down there. I've got Vm is Vp plus Vm with respect to P. And everybody just take a minute and think about it there. Which one of those vector triangles is set up properly to express that relationship? The one on the left or the right? Yeah, if we kind of look at it, we want to think about that. I mean, really, what I would focus on what might be a couple of things. I might look at that expression on the right, which is Vp plus Vm with respect to P, and realize that those vectors would be set, what, head to tail when you add vectors? So I might look at that, okay? I also could just look at the overall equation and say, okay, here's Vm. How do I get that same relative motion? Well, I can go up and then down left, and that'll get it, see? So it is the one on the right, okay? So we just want to be sure that we know how to set these things up, okay? So we okay with that? Okay. So just be sure that the sketch matches the equation. So let's have a look on 260. We've still got a few minutes here, so let's start in on this. So let's say we got a car that's going north on I-5 at 25 meters per second. And then we got another car that's merging, coming in off of an exit ramp there at 20 meters per second. And let's say that you're in car B, and car B has the velocity shown at 20 meters per second. And you're in car B, so you're teaching somebody how to drive. You'll remember this first time you teach somebody how to merge, because what they do, they shut their eyes and they step on the gas, and you got to scream at them or something so that they actually look at what they're doing. But anyway, there you go. All right. So let's write a velocity equation that describes this problem statement. What we want to do is, if we're in B, is look at what A is doing with respect to us. And if you're driving, if you're merging, what you're supposed to do is kind of pick out the moving cars in your lane and kind of look at them and figure out where you're going to fit in, right? So what you're going to see from your moving perspective in B is what A is doing with respect to you. So your frame of reference changes a little bit. It's not like you're sitting in a chair on the ground and not moving. You are moving, and you're watching another moving car, and you want to figure out what it is doing with respect to you. Okay. All right. So what's the expression there that represents that sentence? Find the velocity of A with respect to B. How do you write that out? Car B. Okay, the velocity of A with respect to B. Yeah, it's AB, okay? Now, why don't you write up a relative velocity equation that would allow you to solve for that? What three-term equation would you put together that would include that, where you could actually solve for that, make that the unknown and solve for it? Yeah, we want to be sure we get the subscripts right. Yeah, so what are we going to do here? We are going to okay, so we're going to use VA with respect to B. And if we're going to do something like that with three terms, we're going to want the B to cancel out. So that better go there. And what we want to solve for then is VA. All right, with that, that's set up properly with the subscripts set up about right. All right. So there we go. We look at one other thing here. What direction is B going right now? You know, if I'm going to, by direction, I mean angle. Because we got to get into vectors to do this. We figure out that angle right there, what that is. Yeah, I don't think it is. I don't. Okay, and the one thing on geometry is I always draw up sketches and such. You know, when I'm doing it, it helps me to, you know, be real certain that I'm using the right angles there. 43. Yeah, let's see. As I have it dimensioned there, it'd be something a little different. I mean, what's this angle down here? If I just extend that line and I measure down from the horizontal, that's 53. So what do I got up above there?
53 plus 90.
All right, yeah, what I got here, I got a right angle, okay? Because I've got the velocity, which is tangent to the circle, which is perpendicular to the radius, and I've got an extension of the radius. That's a right angle. That's 53. So what's this one going to be? Yeah, 37. Okay.
Lost signs.
Well, what?
Use the lost signs.
Oh,
Yeah.
yeah, okay. Might work. Okay. So there you go. So that's 37 up left. So why don't we do 161 for Wednesday? And whatever that is that the 24th?
And what did you say was due tomorrow?
As far as what's due tomorrow, well, it's 151 and 152, right? Yeah. And that's the 19th, which is tomorrow. Okay, here we go.
Yeah. Do you want to do it?